Okay, we're beginning in chapter 14 in section 14.4, hemostasis. This is not to be confused with homeostasis. Those two terms are very similar in their spelling, but they are two very different processes. Hemostasis, as it indicates on the slide here, is how the body stops the flow of blood from damaged blood vessels. And note that typically we talk about this from the standpoint of damage to generally smaller blood vessels. 3 steps involving the process of stoppage of bleeding from small blood vessels called the vascular spasm. We'll talk about each of these in more detail in just a moment. At the same time that occurs, platelet plug formation takes place, which of course involves the platelets forming literally a plug to stop the loss of blood from the damaged blood vessel. And oftentimes, if it's a small blood vessel that's been damaged, steps 1 and 2 may be all that's necessary for hemostasis. But if there's more significant damage, then the 3rd step, blood coagulation or clotting, might be necessary. But each of these 3 steps or sequences of steps. First, again, vascular spasm. So let's assume there's been some sort of damage done to the body and some significant rupturing of a blood vessel has occurred. Along with that, of course, would be tearing of blood vessels within which the smooth muscle layer, which we'll get into blood vessels coming up in the next chapter in cardiovascular, but arteries, veins, arterioles, venules have, in addition to the endothelium, additional layers of connective tissue and muscle beyond that initial endothelium made up of simple squamous. And so if we have damage or a cut to a blood vessel wall, and that smooth muscle has been damaged, one of the first things that happens is this spasmic vascular contraction of the smooth muscle. And that, of course, will result in constriction, ultimate constriction of the blood vessel, which indeed lowers the amount of blood being lost through that ruptured cell or ruptured wall of the blood vessel. Now, as I said a few moments ago, at the same time that the smooth muscle is spasming in that damaged blood vessel, there are platelets within the blood that, remember, we talked about earlier in one of the earlier voiceovers, is tending to stick to any exposed collagen, which is typically, again, a constituent of the blood vessel wall. Those platelets will start to adhere to one another and form what's called a plug. And so again, imagine a damaged blood vessel, torn smooth muscle, also torn connective tissue, which is made up to a large extent of a material called collagen. And so that exposed collagen is what the platelets begin to stick to, and they begin to accumulate one behind the other, forming this little plug. And so between the spasm and the plug, that certainly reduces the amount of blood loss. So here's a diagram that sort of illustrates, again, the presence of both red cells and white cells and platelets within the lumen of this small blood vessel. We're going to focus again on the platelets here and the red blood cells. So here's the damage. The wall of the blood vessel has been torn in some manner, and part of that wall of that blood vessel is a connective tissue within which collagen is embedded. This is a protein. So the collagen is what these platelets initially begin to stick to, and begin to accumulate one on top of the other. These platelets do, and eventually will form this plug. Now, we also talked earlier in the chapter about how platelets also have the ability to produce this chemical called serotonin, which, as you remember, causes further contraction of the smooth muscle. So we have the spasm taking place, right, at the same time as the platelet plug is forming, but the presence of serotonin released by the platelets as they begin to accumulate and form this plug sort of promotes additional contraction of the smooth muscle. Again, the goal is to reduce the loss of blood from the damage. And there we have the platelet plug formed. We don't really see the vasospasm so much here, but that has taken place as well. Now, if again we had a more significant amount of damage done, then we might have to rely on this third pathway of hemostasis, which is referred to as blood coagulation or blood clot. This is a complex mechanism involving a series of chemical reactions. Each one activates the next reaction in this series. You'll see what I'm getting at in just a few moments. But if you think of it as a cascading series of reactions that culminates ultimately in the formation of a clot, that's basically what coagulation involves. And this doesn't happen instantly. It may take several minutes from the time the injury occurs to the time that blood coagulates. So it's a little more time consuming. The book introduces two different types of clotting, extrinsic and intrinsic. The major difference between the two is that extrinsic clotting occurs when blood comes into contact with a foreign surface. Or it could take place if there is damage done to the blood vessel. Intrinsic clotting occurs in the absence of tissue damage, when blood comes into contact with a foreign surface. Now, one of the best ways that examples I can give you to think about with regard to intrinsic versus extrinsic, if I were to pour blood into a glass jar, it would eventually clot. And that results from intrinsic clotting, where the blood comes into contact with a foreign surface. That's the glass of the jar. If you had damage done to a blood vessel due to an injury, that's going to induce extrinsic clotting due to, again, damage to the tissues or from a broken blood vessel. However, that's not to say that your blood could not clot intrinsically. Now remember, we said a moment ago, intrinsic occurs when blood comes into contact with a foreign surface in the absence of tissue damage. Now, I'm not suggesting your blood comes into contact with glass in your body like it does in the jar, for example. But what if your blood came into contact with a foreign surface like plaque that forms, let's say, in the wall of a cardiac blood vessel? We know, as we'll see in a little bit too, I'll show you some photographs, of plaque buildup as a result of cardiovascular disease can cause a thrombus to form, a stationary blood clot that could occur in the heart, one of the coronary blood vessels, or it could occur in the brain, and the result would be either a heart attack and or a stroke, respectively. So your blood can clot either extrinsically or intrinsically, but again, if there's damage due to an injury, then we're talking extrinsic clotting. If blood comes into contact, let's say in your body, with a foreign surface, that being a fatty plaque due to eating too many ice cream cones and fries, then your blood could form a clot due to intrinsic clotting. But whether we're talking about extrinsic or intrinsic, both involve a cascading series of reactions culminating in the formation of a clot. And the clot formed extrinsically looks the same as the clot formed intrinsically. This table points out the 12 different clotting factors. Now, if you look on the left-hand side, where we give each clotting factor a Roman numeral, you'll notice that there are actually 12 listed, but this is Roman numeral 13. So where are we missing one? Well, if you look really, really close, you'll see that there's no clotting factor number 6. We go from 5 to 7. Initially, they thought they had a clotting factor which was assigned a value, number 6, but that has since been removed. We don't have a 6th clotting factor, and that's why, for some bizarre reason, we continue with the naming or numbering from 1 to 13. There's just not a 6. Anyway, notice that these 12 clotting factors, most of them, all but 2, are synthesized in the liver. They're formed in the liver. So your liver plays a really, really important role, not only in recycling red blood cells like we learned about earlier in the chapter, but also is a source for 80% of the clotting factors responsible for both extrinsic and intrinsic clotting. And that third column, of course, tells you, for example, clotting factor number 1, fibrinogen, which you might remember is one of the plasma proteins. That's involved in both extrinsic and intrinsic clotting, while others, like say clotting factor 3, may be only involved in extrinsic, while say number 9 and 8 are only involved in intrinsic clotting. So it kind of depends upon the clotting factor as to whether it's involved in both or one or the other types of clotting. I want to draw your attention also to clotting factor number 4. This is calcium ions. We've talked about calcium a lot, how it's involved in muscle contraction, how it helps to build strong bony matrix in bone, right? Well, we also mentioned that calcium plays an important role in blood clotting. It is one of the clotting factors. And of course, we get that from the foods we eat and of course from storage calcium in the matrix of compact bone as well. So even though these two mechanisms, extrinsic and intrinsic clotting, do occur under special conditions, both of these mechanisms employ the last same series of reactions, which involves the conversion of fibrinogen into fibrin. Again, the earlier voiceover talked about fibrinogen. I mentioned to you in that voiceover that the suffix OGEN meant what? It means inactive form of the protein. So this is floating around in your bloodstream as a clotting factor. And if the need is there to convert that, if there's damage to the blood or if it comes into contact with a foreign surface, it will be converted into fibrin, which are sticky, thread-like proteins. And it's the fibrin mesh that will trap the red cells and the white cells and the platelets and form what you would recognize as a clot. So let's take a look at the first few reactions taking place here in extrinsic clotting, which again, as the box indicates, occurs if there's damage to a blood vessel. We start off with the tissue damage, the tissue releasing a chemical called tissue thromboplastin. You don't need to know the name of that particular chemical, but notice that it is formed in response to the damage done to the tissue, and in the presence of calcium activates another clotting factor in the bloodstream called clotting factor 7, and in the presence of calcium activates clotting factor 10, which in the presence of clotting factor 5 and more calcium activates what's called prothrombin activator. So this is what I mean by a series of cascading series of reactions, set of reactions, one behind the other. It has to occur in a certain sequence with the ultimate formation of this compound called prothrombin activator. This is a compound that is synthesized by platelets, prothrombin activator. And the amount of prothrombin activator produced by the platelets is directly proportional to the degree of tissue damage. So if you have a more significant injury, you're going to have more prothrombin activator produced than if you had, say, a minor little sliver or a little cut. And this process of more prothrombin activator being made in response to more tissue damage exacerbates or promotes more clot formation. And so we talk about clotting or blood coagulation being a positive feedback mechanism. We've talked a lot about negative feedback. Most homeostatic mechanisms employ negative feedback. If your body temperature goes up, what do you want to do to it? You want to bring it down. If your blood sugar level falls, what do you want to do? You want to bring it up, right? You have that narrow window that you want to be in physiologically. So we take steps to negate the change. If it goes up, we bring it down. If it goes down, we bring it up. In positive feedback, what are we doing? We're exacerbating. We're pushing the boundaries. We're pushing it more in the direction of the stimulus, but not for a long period of time. It's for a very short period of time. And we mentioned earlier, I think the first or second class, that childbirth was a result, or employed, I should say, positive feedback, as that contractions became more strong and more prolonged as the moment of birth arrived, right? The same applies to blood clotting. We're going to have acceleration of this clotting mechanism, but not for a very long period of time, because you don't want clotting to be spontaneous in the body. You want to have it happen just at that particular site of injury to stop the bleeding. So again, positive feedback is very, very short in its time, because if we were to do this for a long period of time, we'd be doing what? We'd be going away from homeostasis, right? We'd be promoting unstable conditions, and we don't want to do that for very long. We want to just do it for a short enough period of time to birth that baby, or to, in this case, form the blood clot and stop the bleeding. So here's our prothrombin activator that we just left with on the preceding slide or so. Released again in proportion to how much tissue damage there is. That prothrombin activator, in the presence of calcium, is going to convert clotting factor 2, called prothrombin. And I do want you to know the name of all of these chemicals here in this slide. So know what prothrombin activator is and when it's produced. Know that it converts prothrombin into thrombin. These are, again, two different clotting factors, but this is helping to get converted now, 2 into 2A, in the presence of prothrombin activator. And then factor 2A, or thrombin, is going to convert fibrinogen into fibrin. This, remember, is that inactive plasma protein, OGEN, inactive. Now we're going to activate it. Well, what's going to activate it? The thrombin is going to activate it. It's going to convert the inactive form into the active form of the compound, the protein. And these fibrin threads you're seeing in this electron micrograph as these yellow mesh-like strands. And of course, what are they doing? Well, first of all, the fibrin threads are getting strengthened and stabilized by an additional factor. This one you don't need to worry about, but do understand what fibrin is and how it acts to trap all of these red cells. Of course, it's going to trap white cells too, and it's going to trap platelets as well. But as these get trapped in that mesh, right, it's going to form what you would recognize or define as a blood clot. That's going to stop the bleeding. So here's extrinsic clotting. We've taken the last few slides and we've combined them into one single slide. And again, you don't need to worry about the first half of this in terms of the different clotting factors and what gets converted into what gets converted into what. But know the bottom third of this diagram. Know what prothrombin activator is, again, and its role in helping convert prothrombin to thrombin, and then thrombin converts fibrinogen to fibrin. And then, of course, we form our clot. This also fits into the whole entire equation, if you will. So it employs, again, initially some very different clotting factors, doesn't it? Hegman factor 12 and factor 11 and 9 are unique to intrinsic clotting, which, remember, occurs if blood comes into contact with a foreign surface in the absence of tissue damage. But notice that that these various reactions do merge into prothrombin activator, just like extrinsic does. So this bottom part of the mechanism, of course, is shared by both mechanisms, extrinsic and intrinsic. The initial part of the processes, of course, do differ with regard to the different clotting factors. This table simply reviews the 3 different steps of hemostasis. So you can check that out. There's a little YouTube video you can watch as well. So let's assume we formed the blood clot. A couple weeks have gone by. We have to eventually remove that clot. We've got to repair that tissue damage too, don't we? So this slide is going to talk a little bit about the eventual fate of blood clots. We want to not have them there for longer than we need them. So we've stopped the bleeding, and in addition to serotonin, remember, that was released by platelets to stimulate smooth muscle contraction, here's another function of platelets later in the process, which hastens and promotes the repair of that ruptured blood vessel wall. So here we've got this chemical called platelet-derived growth factor, or PDGF, released by the platelets at the site of the blood clot, which is going to promote the formation of additional smooth muscle cells and fibroblasts. So the smooth muscle, of course, is going to have to be renewed in terms of a particular layer within most blood vessel walls. And fibroblasts, you might remember, is one of the more common connective tissue cell types. These were the ones that, remember, acted to produce collagenous, elastic, and reticular fibers, basic constituents of connective tissue. So we've got to repair the damaged wall of the blood vessel. We've got to repair the smooth muscle, and we've got to repair the connective tissue. And these cells help to do that. Once we've got those various parts of the blood vessel repaired, we want to begin to dissolve the clot. And interestingly enough, the fibrin threads, which we remember was the landing net, if you will, that trapped all those red cells and white cells and platelets to form the clot initially, the time will come when these threads will begin to absorb another plasma protein, which we haven't talked about yet. It's in very small concentrations, called plasminogen. What does OGEN mean, remember? Inactive form, right? Well, what occurs here? Once the fibrin threads absorb this inactive form of the plasmin, called plasminogen, the surrounding tissue cells that were initially damaged are going to release what's called plasminogen activator. And as the name implies, it's going to activate plasminogen. It's going to take the inactive form of the substance and convert it into the active form of the substance, called plasmin. Okay, so as the repair process is taking place, there will come a point in time when the damaged tissues will release plasminogen activator. That will help convert plasminogen to plasmin, and then the plasmin will start to digest and dissolve the threads, the fibrin threads, which are of course associated with the clot. We talked a little bit earlier about how if blood comes into contact, let's say, with an abnormal substance, like glass, that it would induce intrinsic clotting. But we also said that intrinsic clotting could occur in our bodies if our blood came into contact with a foreign surface, like plaque that may have built up in the inner wall of, let's say, a blood vessel of the heart or even in the brain. And so stationary blood clots that occur as a result often of atherosclerosis, or in the olden days they used to call it arterial sclerosis, hardening of the arteries, was often associated with older age, poor diet, plaque formation. I'll show you some pictures of this in just a moment. But that would induce intrinsic clotting there at that particular site, be it in the coronary blood vessel or in a cerebral blood vessel of the brain. If that stays there, that stationary clot is called a thrombus. But sometimes it can break off, the bloodstream can kind of dislodge a piece of that, and it can start to float away, a chunk of that clot, and it can be carried throughout the body, in which case we would call that wandering clot an embolus. And you don't like those. Wandering clots are dangerous. Because if that wandering clot were to plug up one of the important blood vessels of the heart, or even some of the pulmonary blood vessels leading from the lungs to the heart, or if it occurred within one of the blood vessels of the brain, it's going to block blood flow, won't it? So imagine this bigger chunk of clot flowing through, let's say, the brain, some of the blood vessels of the brain, and remember, as those arteries get smaller and smaller and smaller approaching the capillary bed, what if a bigger clot of blood started to wedge itself within a coronary or a cerebral blood vessel? Anything downstream of the blockage is going to be deprived of blood, and that could induce a heart attack or a stroke. So again, wandering clots, not good. This often can induce a heart attack too, this pulmonary embolism, where one of the blood vessels that are supplying blood to or from the lungs become blocked. That can cause a heart attack. So here's a cross-section of a normal-looking arteriole. So this is sort of sandwiched between an artery and a capillary bed, an arteriole is. And we can see the lumen here. This is, of course, where the blood would be flowing. This is the endothelium, the simple squamous, shown here in dark pink. Here would be some connective tissue and some smooth muscle. And here's the very outer edge of the blood vessel here. Nice, large lumen, healthy-looking arterial wall. What happens now as plaque begins to accumulate here in the wall of the blood vessel? Notice how much reduced the lumen is. It's significantly reduced from the previous slide, and we have a much thicker layer. This is not normal connective tissue, okay? This is fatty lipid plaque. And as we said earlier, if blood comes into contact with a foreign surface, and this would be considered a foreign surface, that could induce intrinsic clotting. If this is a coronary blood vessel, it could lead to a heart attack. This is in the brain, this could lead to a stroke. And here's a very extreme example of plaque formation. Look at the diminished lumen here in white. Look how thick the plaque is. Wow, that's just astounding. This slide talks a little bit about how clots generally don't form routinely in the body. It's only when we have damage or come into contact with a foreign surface that we would have clotting. And the reason that we don't generally have spontaneous clotting in the body is due to a number of different things, not the least of which is the speed of the flow of blood through the body. There's not enough time to accumulate these various clotting factors and induce the cascading series of reactions that we know culminate in the formation of the clot. So having the speedy flow of blood alone can help reduce the formation of a blood clot. Also, in our plasma, we have something called antithrombin. Now, you might remember thrombin was one of those clotting factors we talked about a few moments ago. It was what converted fibrinogen into fibrin, the fibrin being the landing net, mesh. So antithrombin, of course, as the name implies, kind of counters thrombin. So this is going to limit thrombin formation ordinarily in healthy individuals. So it's only when blood begins to slow down or even stand still or stop moving that we would run an increased risk of these clotting factors accumulating in certain concentrations that we would induce clotting. So the speed of blood, the presence of antithrombin in the plasma, all of these conspire to help reduce any likelihood of spontaneous clotting. The smooth lining of the blood vessel wall, now this is of course assuming no plaque, that alone can also inhibit clot formation. The formation and release of heparin by basophils can also reduce the likelihood of clot formation. Remember, heparin thins the blood. What it's really doing is it's interfering with prothrombin activator. If that doesn't form, remember, you won't be converting prothrombin into thrombin, and thrombin won't convert fibrinogen into fibrin. You won't get a blood clot. So this is just another example of a series of different factors that can inhibit the formation of blood clots. So in you and I, in healthy individuals with undamaged tissue, with not any plaque formation, they all work together basically to prevent any sort of spontaneous blood clots from forming. Your book has an interesting clinical application box. I'd like you to check it out. It's in the very end of chapter 14 on page 549. It's referred to as deep vein thrombosis. I'm going to just ask you to look that over. Kind of interesting. Something to be aware of if you're taking a long flight. And I also want to mention that when you go into the Blackboard course shell under the content part of the menu, I would like you to read over that article that I've got posted entitled Maggots and Leeches Make a Comeback. I think you'll find that kind of interesting. There's also a very interesting YouTube video on the use of maggots in medicine. It's a little gross, but it's really, really cool. So I want you to check out that hyperlink and watch that too. I think you'll find that to be kind of fun. A little gross, but fun. And the last thing I'm going to leave you with is an interesting story that a student in A&P gave many, many years ago. We were talking about blood and blood clotting, and he said his cousin had this birth defect whereby his thumb was fused with his index finger. It was something that needed to be surgically repaired. And so the boy was taken to a hospital in Florida, and there's the link to Paley Institute. You can check it out if you want. And they specialize in these sorts of surgeries. So the boy, who was I think 6 or 7, this is a photograph of obviously his hand, and he had the separation of the thumb and index finger, and they used medicinal leeches here to help dissolve the blood clots and help renew the formation of additional blood vessels here in his fingers, which hastened the recovery process. So, you know, even though the medicinal leeches have been used for many, many, many hundreds of years, actually, we even use them today in certain instances. They're the best tool to help repair clot-related and blood vessel injury-related things. So, kind of interesting.